In my previous video on PWM, I showed you how to generate a voltage with the PWM and how to vary that voltage with the PWM by simply putting, or by changing the PWM, by simply putting a filter like this, an RC filter, on the output of the PWM signal. And what it does is it filters out, first of all, the PWM frequency, but it essentially just averages the on time versus the off time throughout all of the cycles of the PWM signal. And so in this case, for example, the on time is very short and the off time is very long, and so the voltage coming out of here will be low. And conversely, here where the on time is much longer than the off time, the voltage will be high. And if the on time is like 100% duty cycle and it's always on, then the output here will be the same as the voltage at this output of the microcontroller. And of course the lowest voltage it can reach is when the microcontroller voltage goes to 0. And so that's essentially how it works. And then I showed you how to create a sine wave like this by outputting different values to the PWM to change the duty cycle. And so that the duty cycle represented the different voltage levels as the sine wave changes from going from 0 to the maximum. This would be, in this case, with the microcontroller I'm using, this would be 5 volts, and this would be 0 volts down here. Now that method I showed you in the software, if you've had a chance to look through my code, is a very crude way of generating this sine wave, and virtually impossible to easily change the frequency of the sine wave. If you really wanted to. You could change the amplitude of the sine wave by changing the values in the table, but you won't be able to change the frequency. So in this video I want to talk about a method of being able to vary that frequency. Of course the frequency will vary within a range. It can't go any higher than, well, theoretically any higher than half of the PWM frequency, so 62.5 kilohertz, or half of that would be the maximum frequency you could generate in this method, although I doubt that you could even get that high. But with this kind of a PWM frequency, you could probably generate signals up to maybe 3 kilohertz, or a few kilohertz anyways. Now the method I'm going to describe is called direct digital synthesis, or DDS. You can look it up online, there's tons of stuff out there. And if you remember looking at the software, I had a table that had different values starting at I think 128 here, and up here was 255, and down here was 0. And those numbers just varied through the table all the way along here to give you the different values of the voltage. And what I did to generate that sine wave in my first example was I simply read one value after another from the table and output it every time the on every cycle of the PWM. Now there's 256 points of data all the way around this sine wave here to create one cycle, and it's running at 62.5 kilohertz, and you do a simple division, 62.5 kilohertz divided by 256, it'll give you one cycle, and it gives you the frequency of this sine wave that you outputted, which is, in this case, I think it was 244 hertz. Very slow, very low frequency. I'm going to show you a method here where you can actually generate a much higher frequency than that. Now, the way we do it is we have a counter. And in the case of the software that I'll show you in a moment here, we have a counter that's 16 bits long, so it can go from 0 to 65,535, which is 1 less than 2 to the power of 16. And we increment that counter at a fixed rate. And in my example here I chose 50 kilohertz as a fixed rate. It's less than this frequency, but really the two frequencies don't have anything to do with each other. The 50 kilohertz is just how often I update the changes in the duty cycle in my PWM. And so it's actually completely unrelated to the 62.5 kilohertz of the PWM frequency. Although it, again, like I said, this limits how fast or what the highest frequency you can actually generate. So we have this counter that's being incremented, and we simply add a fixed value every, or 50,000 times a second. That works out to 20 microseconds. 1 over 50 kilohertz is 20 microseconds. So every 20 microseconds I take a fixed number and I add it to that 16-bit counter. And then I take that value that I generated and I massage that number a little bit, and I use it as an index to get a value out of the sine table to give me an output voltage, and I put it into the PWM to give me this output voltage. Now if I wanted to create a higher frequency, I can start skipping some of these points here and put only a few of them along this way. Instead of all 256 of them, I can just pick a few off, and the filter will filter out that somewhat, and you'll get a relatively smooth sine wave, but it'll be much faster because we're only taking a few points along the cycle. So that's the way this counter works. We add a value to the counter, and it just, if I just added one each time to the counter, it would just go one sample after the next, and we would generate a very slow sine wave. But if I were to skip some of those by adding a bigger number than 1, then I start picking off, like I said, different points along the sine wave. And you can figure out your frequency that you're going to generate with a pretty simple formula. So the value that you would put, or that you would use to increment your register that you're counting, is derived by taking the frequency out that you want and multiplying it by 2 to the 16, which is the 16 bits of our counter, and then divide it by our update frequency, which is our 50 kilohertz. And that will give you some value that you will increment your 16-bit counter every 20 microseconds, or 1 over 50 kilohertz. And what that's going to do is it's just only going to pick certain values along the phase of this sine wave. And then we put that into the PWM, and it'll produce a voltage at that point, and then it'll produce a voltage here, and another one over here, and one there, and one there, and so on and so forth. And it just does it repeatedly, and that will give you the frequency that you want. Now here we have the output of my filter, and I've set up the software. I've rewritten the code to do this DDS method, and I've put in a number that will give me a 1 kilohertz output frequency, which I don't know if you can see that on the video, but this is 1 kilohertz here. A nice sine wave, that's 1 kilohertz. You may notice though that the output here at the low point hasn't reached the 0 here, 0 volts. And the reason for that is that my filter, the RC network, its cutoff frequency is approximately 1300 hertz. So already the output isn't able to follow the frequency that I want to generate, and that's why it's not going quite down to 0. And also, if you were to look at this, it's not going all the way up to 5 volts either. I would have to change the values of the capacitor and the resistor. In my previous video, I annotated on the video because I forgot to mention what values I'd chosen, but the value of the resistor was 12K and the capacitor was 10 nanofarads. And when you do the math, you get about 1200 hertz as the cutoff frequency. I would have to probably reduce the value of the capacitor or increase the value of the resistor. Is that going to work? No. But as I would reduce the value of the capacitor to get the frequency to go out a bit further. Now I'm going to hop over to the computer, recompile it for a different frequency. I'll put in, let's put in 1200 hertz and recompile it, and we'll see the output change. So just give me a second here. It's now compiling. It's a very short piece of code, so it doesn't take very long. And now I'm burning the software into, or the firmware into the microcontroller, and we should probably see, yeah, frequency's changed. It's gone up to 1200 hertz, and you could see the value here. And you'll also probably notice that this level may have come up a bit, and this level may have come down a bit. Again, we're even closer to the cutoff frequency of the filter. Let's really try something twice that. Let's go to 2500 hertz and see what kind of a signal we get. So just modifying the code, compiling it. Compile is done, and I'm going to burn it. And bingo, there we go, 2500 hertz. Again, you notice how much smaller the signal really is. Again, it's because of the filter. So that's the demonstration of how that works, and let's have a look at the code. Alright, here we are in the software. It looks very similar to the previous one that I did. I just added a few things here. I've created a macro here, and so this is my desired output frequency in hertz. So this was the 2500 hertz that I just demonstrated on the oscilloscope. This is the update frequency of 50 kilohertz. Again, this is in hertz. Here is our sine table, the same as before. It starts at 128, which is the middle point between 0 and 255. And you see how it's increasing in value as you go into the table. Eventually it'll reach 255. And then it'll start to fall off. 254, 53, 52, etc. These are the two registers that are incrementing. I made them 16 bits long. Phase reg is the one that gets incremented every 20 microseconds, or 50,000 times per second. And I created another value here called phase inc. Well, this will be the value that you add to the phase register in order to create the frequency that you want. And right now, the way this code is written, the only way you can change the frequency is by changing this value here and recompiling it. Which is kind of cumbersome, obviously. Unless you wanted a fixed frequency this way, it really doesn't do much for you. In a future video, I want to talk about the UART, which is a serial port, the kind that you can hook up to your computer and use a terminal program and actually type commands, type characters into the microcontroller. And so I'll probably do a video on that and use an enhancement to this software so that we can actually type in 2500 and it'll produce 2500 hertz, or you type in whatever value or frequency you want and it'll actually produce that value. For now, this is just a demonstration of the philosophy of this. Now let's skip through some of this stuff here. Same I/O port for the PWM output. Now we're using timer 0 again to generate your fast PWM, and we're only going to use the output compare register A because we're only using one output this time. Now I need to generate this 50 kilohertz interrupt, and so I'm using timer 2 to do that, and it's basically the same way as I did before to generate the 10 millisecond interrupt in a couple of videos back that I showed you how to use timer 2, I think it was, to generate 10 millisecond interrupt. But this time we just do it a little bit differently to give me a 50 kilohertz update or interrupt, or 20 microseconds between interrupts. Then here we're just initializing our registers. So phase inc is given its initial value. So this is our DDS out, which is the frequency that we want, multiplied by 65,536, and then divided by the update frequency. And that will give you a number that gets added to the phase reg every 20 microseconds. And then in the forever loop here, we're doing nothing because the forever loop, or because the interrupt is actually doing all the work. And let's have a look at the interrupt here. So this is now timer 2's compare register A interrupt. Again, the same way I did it with the 10 millisecond interrupt, except we're doing it with a 20 microsecond interrupt now. I created another variable here. It's just going to get used during the interrupt. We don't have to keep it. Last time I created one here which was static because we wanted to remember it, but this time we don't care about this. After we've used it, we just throw it away. So here we take our phase reg and we add the phase inc to it, and all we do is continuously add whatever values in phase inc. We continuously, every 20 microseconds interrupt, phase reg gets incremented by this phase inc value, and it'll overflow. It only goes as high as 2 to the 16, and then it'll start over again at 0 or whatever value it is. And so it just continually runs, continually increments. And then what I do is I take that new value of the phase reg and I just right shift it by 8 bits because I just want to have the upper 8 bits. Now our sine table is only 256 values long, and so that's 2 to the 8th power, so that's why I just want 8 bits. And so I'm just going to take the upper 8 bits of phase reg. If I had a if I had a sine table that was 65,536 entries long, then I could use the whole value of the phase reg as the index into the sine table. But we only want to use 8 bits because our sine table is only 2 to the 8 bits long, so 256. So I becomes the index into sine table, and then whatever value that came out of sine table is the output, goes into the output compare register. And that's all there is to this. It runs very simply. Every 20 microseconds this thing runs, increments the phase register, grabs the upper 8 bits of the phase register, plugs it into the sine table, picks out the value from the sine table and stuffs it into the output compare register, and the PWM will change accordingly. What I've done here and here is I wanted to make some time measurements to see how fast this stuff was running, and so all I did here was I toggled another I/O pin. So here I set the I/O pin, and here I clear that I/O pin, and this allows me to measure how long it takes to do this service this interrupt routine, and I'll show you that on the oscilloscope in a moment as well. So that's pretty simple how we do this. Sometime down the road, like I said, I will show you a way to be able to manually, while this code is running, to change the value in phase inc, so we can change the frequency being output by this thing on the fly instead of having to recompile it every time. But for now, this is a good demonstration of how it actually works. Now, there are some concerns of mine here, because I'm starting to push the capabilities of this microcontroller. It's just a simple little 8-bit microcontroller. The ATmega 328 is a pretty good little device, but it has its limitations. And so when you interrupt it 50,000 times a second, it doesn't have a lot of time to do anything else. And I just wanted to make sure that it was capable of doing what I wanted to do and have enough processing power left over to do something else, which is, in the future case, read the serial port and process the characters being received in the serial port to generate a value for your phase inc register here. And so let's have a quick look at the timing here. Now I just moved the scope probe over to that pin that I'm toggling with every interrupt, and so the timing between here and here, this is one interrupt, this is the next interrupt. So you can see on the frequency shown there, it's about 50 kilohertz, which is what we expected, because that's what I decided my interrupt rate would be, is 50 kilohertz. And then we look, and so the time in between when this line goes high and it goes low is when it's actually processing the interrupt. It's actually the timing is going to actually be a bit longer, because it takes the processor some time for it to actually go into the interrupt service routine, and then when it leaves the interrupt service routine and gets back into the main code, which in this case is doing nothing but sitting in a while loop, it takes a couple extra cycles as well. And so from between this falling edge here and this rising edge again for the next interrupt, there's quite a bit of time here. So there's 5 microseconds per division, so we've got 5, 10, 15, 20 microseconds, which is what I mentioned before. This is how often the interrupt's going, every 20 microseconds. So I got a bit less than 20 microseconds to do quite a bit of stuff in here. The microcontroller will execute one native instruction. Most native instructions for the microcontroller will execute in one clock cycle, which is 1/16 megahertz, and I forget what that is in time off the top of my head right now. But it works out to approximately 320 instructions, native instructions, between interrupts. And so my concern was that it was not going to have enough time to do anything here, but I think I'm pretty comfortable now that we'll have plenty of time to do that. In fact, if I needed to get a higher frequency, I could increase the 50 kilohertz to something else. I could make it 100 kilohertz, which would produce the pulses here, and still quite a bit of time in between to do some processing. Right, back in the code again. Let's have a look at the listing file here. So this is the assembly code, or the actual native instructions that the microcontroller produces. Here is the interrupt service routine, and so it goes from this point here all the way down to there. So these are all the native instructions that the compiler has generated in order to do all of this stuff. So that's what you were seeing is the pulses on the oscilloscope. So this is the instruction that tells the I/O port to go high, and then this is the other instruction that tells the I/O port to go low. Now I said there was a bit of overhead after the interrupt occurs. It takes a moment. It takes some time. I wouldn't say a moment, but it takes nanoseconds for the microcontroller to actually respond to that interrupt and generate the vector to start at this instruction here. And you can see it's doing a bunch of stuff before it even gets to the point where it sets the I/O port high, or sets that pin high. And at the very end of all this, this is where it sets the I/O pin low, but there's all of this stuff done here before it actually gets back into the main routine again. And so the actual interrupt service routine time is a bit longer than what I was showing on the oscilloscope. But still, in between interrupts, there seems to be plenty of time to do a lot of stuff. So, another quick video on another interesting technique. I don't think I showed you any kind of cool new stuff here about programming, but just gives you a little look at how to generate how to digitally generate analog signals using the PWM. And we don't have to use the PWM to generate analog outputs. We can also use one of the I/O ports and what they call an R2R resistor ladder, which is another type of digital analog converter, which I might show how to use that. It's pretty simple. I mean, the code would be pretty much the same, just where this phase, the sine table output right here, goes to, instead of an output compare register, it'll go to one of the I/O ports to send a value out to out to the pins of the I/O ports, and then the R2R ladder, resistor ladder, will convert it into an analog signal. Alright, I hope you got something out of this video. Thanks for watching, and stay tuned. There'll be some more coming.